All right, we're back. Another file here to solve for this. In order to put this in your calculator and solving for theta, you usually press the second and then the sign button, and it will come up with this inverse sign. You'll see this if you use the Texas Instruments calculator. You put the number in, 0.1, and again we're approximating because I said the wavelength's about 0.2 meters, but it really doesn't matter. This is for theoretical pleasure. So theta will be equal to about 5.7 degrees. Now what does this mean? What does this mean? If we were to have the speakers, so I'll draw some speakers, and the sound's coming out of the speakers like so. So let's, we need two to make this happen, so we'll dupe it. Now put that other speaker here. I just want you to recall that these speakers are separated by some distance d. Which is there. These speakers are some distance away from the screen, the wall, and I'm going to make that wall yellow. Oh, I'm sorry, it's going to be blue. My mistake. If we go back up to the problem, the distance that this speaker is placed from the wall, or these speakers are placed from the wall, will be 5 meters. So we're going to have to deal with some trig here. I understand that can be challenging. The question is, what is the location here or down there where you get constructive interference? And I changed the question slightly. So we said that there is sound when that listener walks. Remember, you get a constructive there when m is equal to 0 because we're off by 0 wavelengths. Then you'll get a constructive here where you're off by 1 wavelength, or you'll, because of symmetry, you'll also be off by 1 wavelength there. So the question is, what is the value of, I don't care, y in this case, and it could be positive y or negative y, how far you are from that central location, 0, that you'll get a constructive interference. Now if I draw some more, and I'll try and use yellow, that distance, actually we'll use red because that's what they used before. That distance is there, or that path is there from that central point, and that angle will be theta. So the question is, if we know that angle theta, which we solved for previously, which is 5.7 degrees, we know this side of the triangle, can we find that side? And this is a right triangle, and this is the hypotenuse. Over here will be the opposite, and this is the adjacent. So if we want to solve for the opposite side, we're going to use the tangent function. Tangent of theta is the opposite over the adjacent. Since we know theta and we know the adjacent, we'll solve for the opposite side. So the opposite side, which is going to be the distance y, how far you are from that central point, will be the adjacent times the tangent of theta. Getting a little singing in the background. My son is singing. Hope you enjoyed that. As much as you enjoy these physics videos. So the adjacent will be 5 meters times the tangent of theta, 5.7 degrees. So we'll get the old calculator out, fire it up once again, and do a little math. You can hear the keys. So I'm going to take the tangent of 5.7, which is 0.00998 or 0.0998 times 5, and it will give me a value when I finally plug this in for the opposite side. That positive y will be about 0.49 meters. And that means, there's a meaning to this, believe it or not. That means if I'm standing here, and I have two speakers which are separated by some distance d, playing that musical note of 1500 hertz exactly, well, almost, because we approximated the wavelength, and this is 5 meters away. If I'm standing here, I hear noise. As I walk away, I'm walking up, I hear nothing, and then all of a sudden I'll hear something, and the distance I would have to walk is 0.49 meters, either up in this direction, that's 0.49, or down in that direction to hear that. Could you predict, and this is a tough question in expansion, how far would I have to walk to not experience constructive interference, but to experience destructive, either up or down on this page? That's right, it's about half that distance, so 0.25 meters. Some other distance up here, you'd have another constructive interference. Some other distance down here, you'd have another constructive interference. So again, these red dots are my constructives. And then in between every constructive, you'll have a destructive, and so on. This is a difficult problem. It's going to take some time to get used to doing stuff like this. Again, practice makes perfect. Let's move on. This is an easy topic, and it's one of the last topics within this chapter. It deals with the interference of sound waves. If you look, you have a teal wave, a light blue wave, and a dark blue wave. And I'm going to pull out the old line tool one more time, and we'll show how these line up. Actually, we have lines set up for us. If you look at this location, the teal line and the dark blue line will line up, so you have positive amplitude lining up with a negative amplitude. If they're equal but opposite, you get 0. Over here, as time goes on, you'll have the waves superimposed. They're going to be in phase, so you get a big amplitude. Over here, they're out of phase, so you get nothing. And if we have these two waves traveling as time progresses, in some locations or times, you'll have situations where there are no waves, and then you have big waves, continued by, as time progresses, no waves, big waves, no waves, and so on. So you'll hear loud, quiet, loud, quiet, loud, quiet, loud. And this is like a wah-wah effect. It will wah 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 wah. And it's because of waves combining. You hear this when you listen to, I don't know, Louis Armstrong. Let's say Satchmo's playing his trumpet. You hear a vibration effect. It's because of the fact that there are many waves being produced within the air columns of that trumpet. And when these waveforms line up constructively, you'll hear loud, and when they line up destructively, you'll hear soft. We can predict the rate at which these wah, 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 the rate at which you hear sound, by taking the difference in the frequency between these two waves. So to find that beat frequency, if we have 500 hertz and 450 hertz combining together, so these waves are traveling and combine with each other, the difference between these is 50 hertz. So that means we'll hear that wah-wah effect, wah, 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 not about 3 times every second. You'll hear it 50 times every second, and that's going to be more than you could even perceive. You would just hear one constant tone. In this case, I think the human ear can only perceive about 10 hertz of beat frequency. And again, when we come back together, I'll demonstrate these for you in detail. Another principle that comes out to play is the Doppler effect. And if we have a truck that's resting and sending waves out, the wave spacing on the back side and the front side are the same. If this fire truck is in motion with some velocity, it's producing waves. As its waves travel out, you get crowding. So on the front side, you'll hear a high frequency. On the low side, actually I'll put a capital F for a big frequency. On the trailing side, you'll hear a low frequency. So you hear this when a train goes by you, or a jet, or a siren, and so on. All waves obey the Doppler shift. and you'll have to be able to predict the relative frequencies. Again, we're using the algebra base just as an introduction. While I'm not present in class, we'll come back and hit this in more detail. So when something's moving towards you, you hear a shorter wavelength, a higher frequency, and when it's moving away, you hear a lower frequency. And we've all experienced that in our daily lives. So if you were to drive toward that sound source, if this is a sound source, you would hear high-pitched sound. If you drive away from it, you're going to hear low-pitched sound. Another thing you could do is to have the sound source move toward the observer sitting in the car, and they would hear high pitch. Or if this sound source goes away from the observer, you'll hear a low pitch. So it's relative motion. You could have one or both of them moving. If we have a stationary object, the wave spacing in every direction is going to be constant. If it moves slowly to the right, the waves will be slightly crowded on the right side and not as crowded on the left-hand side. If that object moves with a similar speed, if this object moves with the sound waves at the speed of sound, you're going to have an entire bunch of waves crowding on the front, and you get what's called a constructive interference at that location. It creates an area of high pressure. This is like the sound barrier, and if you exceed the speed of the waves that you're producing, you're going to get this thing called a bow wave. We've seen this behind boats, where boats are traveling faster than the water waves they produce. So the bow waves are usually V-shaped waves behind the boats, and supersonic shock waves will occur when this plane travels faster than the speed of sound. So in summary, sound are waves. They're longitudinal waves that we know already from our previous studies. The pitch is the frequency, the loudness is the amplitude or the intensity. Stringed instruments produce standing waves, and stringed instruments will produce standing waves in F, 2F, 3F, and so on, because they have nodes at both ends of their standing waves. Musical instruments that have tubes with two open ends will produce frequencies at F, 2F, 3F, and so on, all the way on. So I'll draw two open ends. Musical instruments that have one open end will produce frequencies at F, 3F, 5F. Next would be 7F, 9F, and so on. So they produce musical instrument or tones at various harmonics. Wind instruments have vibrating columns of air. String instruments involve vibrating strings. All sound waves can exhibit interference, and if there's slightly difference, they produce beats or that wah-wah effect, and then we will perceive a difference in pitch when we move toward or away from a sound source, or that sound source moves in similar manners. So again, what I'd like for you to do, and I'll send you an email, is to go ahead and solve the problems in the algebra-based sound chapter. You'll have them. We'll treat this as a formative assessment. And just do your very best for them. If you have any questions or concerns, you can contact me. You can shoot me a text if you prefer. Also, what I'm going to do is to publish the solutions for every single one of those problems online. That way you'll have access to them. Another thing I'll do is to share the test with the solution so you can take the test and then grade your own test. When we come back together, we'll answer any questions that you may have, and we'll sit down and take a test that I know that you'll all be successful with. So again, if you have any questions or concerns, feel free to contact me. You can email me at my email address. It's chestnut.patrick@gmail.com. And again, I'll send you some information on the Wigio, as you should be looking at this already. It's being shared. Again, you're going to do great, and if there's anything you need, contact me without hesitation.